Welcome back to our office. Today we actually have two different lectures we'd like you to visit, and both of them are applications of differential equations. So they both correspond to chapter 9 from the book, and we'll be doing no really new algorithms. So we'll still just be talking about solving ordinary differential equations. But both of these lectures, today the first one on classical chaotic scattering, and then later on, you won't know what day it is, sometime we'll talk about the quantum eigenvalue problem, also done with differential equations. And both of these applications I recommend you look at, maybe study. They're not essential to continue with the rest of the text, but they're very important in practical applications, and they take some of the tools you already know and use them in different ways. So let's get on. Let's talk about chaotic scattering, classical chaotic scattering. So quantum chaotic scattering is another subject altogether, a rather difficult research level subject, in fact, but classically it's a quite easy and important problem. So take a look at the next slide. Easier said than done. There we go. So words, Landau's first rule of education. Know what the words mean. What does classical chaotic scattering mean? Okay, so classical means that we'll use classical dynamics, no quantum effects. Chaotic scattering, well, chaos is very hard to define. It generally means that you have a system which is hypersensitive to the different parameters, the initial conditions, so that even the smallest change sometimes can lead to a very big change in the results. So the smallest change in input, can change the output tremendously. So, where have we ever seen anything like this? Well, maybe you should recall troubled youth. Have you ever played with one of these wonderful pinball machines? Okay, so here, you're not supposed to look at the pictures, okay? So here you have bumpers. And remember that if you shoot a pinball, and sometimes it just has all of these multiple scatterings inside here. Bounces around, boom, 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 boom. Of course, these bumpers here are activated. They jump a little bit when things touch them. So that may have some effect in it. Okay? But what you're seeing when you do that is multiple scatterings, which is a technical term, and it means many scatterings. Okay? And so here you have in classical multiple scatterings. And if you have enough of those, then it seems as if you can get an answer which changes very much depending just on some little small details, like how hard you shook the side of the machine, whether you leaned on it this way or that. And so this is almost classical chaotic scattering. Okay? Everything you know about classical physics means that it's continuous. You can change the position, you can change velocities continuously, and everything behaves nice and continuously. If you have enough chaos, in this case if you have enough multiple scatterings, you can get some very weird effects, and that's what we'd like to look at. Okay? So this reflection, get enough of these internal reflections. In fact, if you can get the pinball to come up here and just, make its path and then bounce back and forth and get trapped so it never really leaves this region, it essentially has forgotten everything else in its early life. It forgot about its parents and the dog it grew up with, and it just, then goes someplace on its own. And that's what we mean by chaotic scattering, classical. So we'll see examples of this. Okay? So then the real physics question is, okay, everybody likes pinball machines, but can you model this with a static ordinary potential? Or does this require some kind of active bumpers like we have here? Well, that's a good problem. So we'll have to answer that. So let's look at the next slide. Okay, so we have both a model and a theory here. The theory is very easy. The model is, well, here we have a potential. Okay, we have this beautiful figure here, somewhat like the grand Tetons, and we want this to be our potential that we scatter from. And it's just a model, nothing very fundamental about it. It just has 4 bumps. Okay, so this is actually the potential. We'll come back. So this is actually the potential as given up here. It's a function of x and y, so it's a 2-dimensional potential. So you're seeing it here in 3 dimensions, the third dimension, the z direction, indicating the height of the potential, the value. Okay? So this is just, there's the equation for it. It's a Gaussian in x and y times an x squared or a y squared. So that gives it peaks in each of these directions. And we imagine here scattering a fairly high energy particle from this potential. And let me say right now, scattering is different from bound states. Much of what you study, particularly in quantum mechanics, but also classical systems, are bound, like the planets. Okay, and it's easy to study the planets to see what's going on. You hardly ever study the comets, okay, or scattering in an experiment, and yet that's what we're talking about here. And in physics, much of what you learn about microscopic, submicroscopic materials, atoms, molecules, nuclei, particles, come from scattering. So it's a different kind of experiment. So here we talk about high energy, and when I say high energy, I mean high enough energy so that the projectile you shoot in doesn't get trapped forever, bound inside. It bounces around and it leaves. So that's what we mean by high energy. We don't mean high enough energy like you get at the Large Hadron Collider, which would blow everything apart. No. Okay. So what else? There's a plus or a minus sign in front of this potential, and that gives you the option of having repulsive or attractive potential. The figure as drawn here with positive V going up is obviously repulsive potential. And we have 4 internal peaks here, and they can give you both scattering and reflection. So what we can have here is a particle coming in, and it obviously, if it has enough energy, it can go up over the peak, and through. If it doesn't have enough energy, it can come up and then roll back. Like Rutherford scattering, in different ways. Or it could, start in the middle and work its way all the way through. Sometimes, if we do it just right, we could have a particle which, sort of comes in here, bounces around internally, bounces through, and then just keeps going around. That would be hard to do, but, and then eventually leave. So this is an interesting case. You can have, depending on the energy and just how you send it in, you can have all different kinds of reactions occurring, all different kinds of scatterings occurring. Okay, so this is our model. The model is a potential. We call it not a theory, it's just a potential we made up because it looks nice and because it has some interesting features which we think might be similar to that pinball machine. Recall, where the pinball machine had bumpers, 4 bumpers. This is our model for bumpers here, but a nice smooth potential which we can integrate. We can solve the equations of motion for. Okay, so that's the model. What's the theory? The theory is just classical dynamics. This is your old friend from freshman physics. Okay, it's no more than F equals ma, Newton's law. This is the potential, so we know we take its derivative, gives us the force. We know the force. We know the mass of whatever projectile we send in to interact with this baby, and then we just have solve for the acceleration. So pretty easy problem. Okay, so let's go on. Let's look at the next slide, particularly where we talk about what is it that you measure in an experiment and what is it that you observe. Okay, so in a scattering experiment, and this is by definition of what we mean by a scattering experiment, we start with a particle which having a known velocity v, and we start with it at minus infinity, okay, far away from wherever the potential is. So far away, in fact, that we can approximate, say that the potential vanishes when we're out back here at minus infinity. So this is the y-axis. So in this case, we're starting at y equals minus infinity. Okay? And the particle we send in, often called the projectile, because we project it in, has some velocity v, and that's known. We're the experimentalists at this moment, so we can control what that velocity is. We can control the type of particle, just what angle we send it in at. We can do that, but we're allowed to do that. So that's part of the fun of being experimentalists. So we do that. Classically, you talk about the impact parameter b. Okay, so that's b here, and here's b in our picture. And what that means is this is the center plane, arbitrary, but this is our x equals 0 axis, and b is just the distance from that axis. So we will vary b to be positive and negative any place. That's something else we can vary. So we can vary, the velocity of the particle and which peak here we wanted to send it to, or send it down the valley in the middle. So we can do all that. Okay, that's what we can do. And then what we do for a living, if you're an experimentalist and you do scattering, is the hard part is you then have to observe what happens. And what you do is you make your observation here by observing the scattering angle. Now you observe the scattering angle not inside here because the potential's still acting, but in some region way far away where you know the potential is no longer acting. So we call that plus infinity. Now obviously in a real laboratory you can't get to minus infinity, you can't get to plus infinity, so we say infinity meaning a distance large compared to the range of the forces that may exist here. But those forces are usually atomic or subatomic, so a few centimeters can easily be at infinity as far as that goes. And then we observe the scattering angle theta. Okay? So here's the scattering angle theta. So what this means here is we have our incident direction coming in here, so that's the y-axis, and then a particle comes out here and we observe it, with some detector here, like an eyeball, okay? And that's the scattering angle theta. Okay, so right there. So that's coming out. We observe that. So we observe the number of particles scattered at some scattering angle, and that's all we have to observe. Okay? Since the target itself can't recoil, because we're talking here about a static potential, we can do this and let it recoil, but it just makes it more complicated. Forget it. No new physics there. So the velocity of the particle doesn't change. Now, the speed doesn't change. The velocity changes because the angle changes. Okay? So we don't even have to measure any speeds. We know what it has to be. We can check. Okay? And what you measure then is the number of particles scattered at each angle. So for each impact parameter, which in a classical experiment you can control, you know exactly where the particle is, you know exactly what the velocity is, you measure all possible scattering angles and how many particles get scattered at each angle, and that's what you plot up. That's your data. Okay, so that's the scattering experiment. That's how you do it. Okay, that's how the experimentalists do it. So let's look at the next slide. So in the next slide, we say, okay, that's what the numbers they write down in their book, but then they have to do something else to analyze the data. Okay, so here's our picture again, the Grand Tetons. And what the experimentalists actually measure is the number of particles scattered into some solid angle, delta omega it might be called, at each angle theta. And we need to convert that into what's called the differential cross-section, here symbolized by sigma of theta. And the reason is you want to be able to publish your results and have everybody do an experiment and compare it to yours. But not everybody has the same detectors, the same size angles they use, the same accelerator that they accelerate the particles with, so the incident flux might be different. So you need something you measure and then you can publish, which is independent of the details of your experiment. Okay? So if you haven't seen this before, don't worry about it. You should read about it in a classical mechanics book. But what you measure is a differential cross-section called sigma of theta, sometimes called the sigma d omega. Okay? But sigma theta is fine. And it's independent of the experimental details. So equation 1 here is actually then the definition of the differential cross-section. And what it says is the differential cross-section is a number. It's a number measured here. So this is your detector. And this detector subtends, that's a nice word, subtends, I always like that. This detector subtends some solid angle, delta omega. Okay? So you measure the number of particles coming into your detector. That's the number of scattered particles. Your detector is at some angle theta, right there. You divide by the size of your detector. That's delta omega, the solid angle that it subtends, because the bigger solid angle, the more particles you get, you want that number you get to be independent of your size. You divide by that size. Likewise, if there's a greater number of incident particles, you'll get more scattered. So you divide through by the number of incident particles. And then you divide through by the delta A, by the area of the target here that's being illuminated by the incident beam. Okay, so here we divide through on the top by the detector size, and here we divide through by the area of the illuminated target. Because a bigger area, you get more results as well. So we divide through by everything, and that is then our differential cross-section. You know, it's hard to understand, but that's the definition of it. Okay, and that experimentally is what's measured, and that's how you present your results. Fine. When you do theory, you need to compare what the experimentalist has measured, the sigma d omega or sigma theta, to theoretical results. And the way you do that is very interesting. You take your theory and you calculate what the scattering angle theta should be for different values of b. Okay? So that is what you're calculating. So if you want, I'll write it down here. If you calculate theta of b, well, I almost wrote it down. Okay? That's what you can calculate theoretically. Once you know that, you can just use this formula, which you derive from looking closely at what's happening. You just take a ratio, b, whatever impact parameter you're at, you divide by d theta dB, so that's how the scattering angle varies with b. That's not an experimental quantity, that's a theoretical quantity, and you divide by sine theta b. And if you do that, you get something which is independent of b, get something you can compare to theory to experiment. Okay, so that's theoretically what you'll do. So we'll calculate theta of b some way, and then we'll compare the two. Fine. We have to go through the theory every now and then just to keep you honest. What's interesting here, what's fascinating here is that this is real physics. Number one, this is how you do a measurement. Real data is what's interesting, so what makes physics different from mathematics. Two, we have a theory. We have a theoretical formula to compare with. Classically, it's very nice. Quantum mechanically, you have to compute it very differently. But you can see something of great interest here. There's a derivative, d theta dB, in the denominator, and that can be most anything. That could be 0. If it ever gets to be 0, then the cross-section blows up. Very unusual, but you'll see things like that happening. Or it can have discontinuous behavior, which you'll also see happening, in which case the cross-section has discontinuous behavior. Both of those instances I've discussed are related to chaotic scattering. So this is an indication of where we can get chaos from this kind of behavior of just these derivatives. So interesting. So let's get on and talk about what we have to do and how we do it. More theory. We better take a break. Okay. Theory. All we have to do is solve Newton's law to solve this problem. So it's actually very easy. Okay? So we have Newton's law in the xy plane. So this is interesting for a couple of reasons. One, because we're solving a system in 2 dimensions simultaneously. And second, because it's so easy. It's just F equals ma. So here we have F equals ma. It's a vector equation. In the x direction, we have m mass, d squared x by dt squared. And we have, x here is a vector x, so that has all the components. So there's the force in the x direction, the gradient of the potential, that's its x component. This is the force in the y component. So that's it. So for example, here in equation 2, I write down, there's both x and y, same thing. Okay? So that's the x component, y component. Here's the common factor out front. This is the x force. This is the y force. So that's it. Just taking the derivative of that potential, and we have 2 simultaneous equations. So equation 3 and 4 are, in fact, in red. To remind you, this is what we're trying to solve. These are the differential equations. So we have equation 3, which is the motion in the x direction as a function of time. Equation 4, which is what we have to solve for the motion in the y direction. So we have more complicated differential equation than we've solved before, more complicated in the sense we have 2 simultaneous second-order differential equations to solve. I'll say that again. We have two simultaneous, means they have to be solved together. Second order because there's the second derivative and the differential equations. We have to solve them simultaneously, and we solve them for position as a function of time, x position and y position, and then we can remove the time, which appears as a parametric variable, to get x as a function of y, or y as a function of x, either way. So those are the equations we have to solve. And we know how to solve differential equations. If you don't, go back to earlier lectures or read the book. Now let's solve them. Let's look at this next slide. So this next slide, we say we have an applet. I'll show you that in a moment when we see how the equations pan out, which actually solves this for you and shows you some of the physics we're going to get. We have to now solve the differential equation, two simultaneous second order, and recall we've used RK4, the fourth order Runge-Kutta, as a very robust, accurate way of solving equations. And when that solves ordinary differential equations, it takes a second order equation, a single second order equation, and breaks it into two simultaneous first order equations. And we now have two second order, so we're going to end up with four equations, first order. And from that, we have to produce a trajectory. So the trajectory, which is x and y as a function of time, will be our solution. It'll have two components, and we'll have to solve four first-order equations. So remember here, in the general form, Runge-Kutta just says dy by dt, the first derivative, y being here just an unknown variable, not the position y, just the unknown. T is the dependent variable. T is the independent variable. I said it backwards. Y is the general dependent variable. T is the independent. We vary T. The right-hand side of this equation is capital F, vector F. That's the force function. Have to have four components here. And Y will have four components. The first two are always the easy ones, so we'll define them, which is x and which is y here. Doesn't matter. Y0, we start counting at 0, is just going to be the x position. Y1 is the y position as a function of time. And then Y2, the third y is just the velocity in the x direction. Y3 is the velocity in the y direction, dy dt. So those are the four variables, and now we just have to express, our differential equation in terms of those four variables and deduce what the force function is. So if we do that, you've done it before, it's quite straightforward. The first force function, the F0, is just going to be, it's the second derivative, so that's just that's x dt here, which comes in, okay? And the first F1 is just going to be y3, so those are just the two derivatives. Then the actual forces appear here in F2 and F3. So here we have the equations to solve. We have to express equations 5 and 6 remove the x's and the y's and use y0 and y1. I did not do that in writing it down here because then you'd have to get a stiff neck looking back and forth to see all the different possibilities. So here you can see just the usual force in the x direction here and the usual force in the y direction there. The plus and minuses correspond to what was plus and minus in our potential. Plus was repulsive, minus was attractive. Here it becomes minus and plus because there's a minus sign when we take the derivative of the potential to get the force, so it reverses it. Fine. Let's see what the solution of these equations look like. Yes, allow the applet. Aha. So here's our chaotic scattering. So this was an applet written a while ago by Manuel Paez and his group at the Universidad de Antioquia in Colombia. And what you can see here is the same thing we've been talking about here. Surprise, surprise. Here's the impact parameter B. Here's the particle coming in along the x-axis here. Scattering angle theta as before. And here are the grand tetons in a little bit different color. But it's the same idea. This is what's going to be a scattering. And now here we have a model. So here are 4 disks, and they just represent the peaks of these potentials to give you an idea. And you can control whatever you want. You're the experimentalist. And some of this is in Spanish, so not a problem. Here we have repulsive potential or attractive. This is the mass, this is the velocity. These are the different impact parameters. And for different impact parameters, starting from minus b to plus b, this will show the scattering. So let's start it. And you see here, this is now the impact parameter varying. So the particle is moving up, and its repulsive potential, and it's getting reflected back. Ooh, but sometimes it gets through. And then, we're still moving up here very slowly. These keep going through all the time. And then you can see, aha, they're getting through, they're being bent, they're being sort of focused, but then they start hitting the edge, and they bounce all over the place. That's chaotic scattering, okay? Suddenly, the smallest change in the impact parameter here is giving you a very large change in the scattering. That's classical chaotic scattering. So we could stop this and say, okay, 2 interesting things. One, if we look here, this is the scattering angle theta. This is the impact parameter b. And remember I told you if that has funny derivatives, d theta, db, then we'll get very funny cross-sections. And you can see here, ooh, this thing just jumps at some impact parameter. It jumps discontinuously. Here it jumps again. That will give us very unusual experimental cross-sections. So it's really an experimentally observable effect. If we now say, let's look at an attractive potential, attractivo, and just start this again, what you see is here the particle is attracted, so sometimes they get nearly trapped inside. And if the particle really got trapped inside, it would be a bound state. But it has too much energy for that. But you can get these long coils where it just bounces internally like a pinball machine. Hey, so this model's working. And that's chaotic scattering. And you can see here it's coming through, it's getting attracted in, and then once it gets attracted in, it nearly stays inside, nearly gets bound. And so here too, it's scattering, and you're getting these discontinuities in the scattering angle versus impact parameter. So let's get back. So that's what we're aiming for. That's what we want you to solve for by solving these equations. So that applet, it just solves the same 4 differential equations using a Runge-Kutta technique. May not be as accurate as you can get, but it works very well. Okay, so how do you do this? Did I skip anything? Nope, everything's there. What do we want you to do in your problem? So we want you to use RK4. Use the Runge-Kutta 4th order. We want precision. So make sure this step is small. We'll give you some hints what that should be in the text, but it should be, quite small, so any peculiar features you get, are a function of the physics, the mathematics, not of the numerics. Okay? So start off with initial conditions. No velocity in the x direction. Okay? So that's, in this case, that's perpendicular. We just want to shoot it straight along the y-axis towards the target. Vary the impact parameter. Vary it fairly small steps like we just saw so that you won't miss any of the interesting physics, because after all, some minuscule change in the impact parameter can lead to very different results. That's what you want to see. So vary b between -1 and 1 for the values I've given you. Here's a typical mass, typical velocity. The interesting thing is what you'll get output will be x as a function of time, y as a function of time. Put them together so that what you can plot up is the trajectory. And I want you to see what the trajectories look like. Both if you want as a function of time, like we showed you now, but that's an animation, but just the individual trajectories is fine. Just, each one for different values would be. You can do lots of graphs. You can put them together in one way or another. What you want to see, what you don't want to miss, are those cases where you get backward scattering, like from repulsive potential, but even from attractive, when it goes around enough and comes out, and high multiple scatterings. That's where the interesting physics arise from. One thing I also want you to do, point 5 here, is look at phase space. Remember phase space from when we did the pendulum? If you haven't done the pendulum yet, we'll see it there too. Pendulums are bound states, and the phase space orbits for pendula, for harmonic oscillators, were ellipse-like figures. Here, the phase space, which will be x as a function of time and x velocity as a function of time, these will be not like bound states, which are like the planets. These will be like the comets. So these will be open figures, parabola-like, hyperbolized-like figures. You should see what they look like. It's interesting. It's a different type of physics. I just answered question 6. How does scattering and bound states differ? Well, that's how they differ. One's open orbits, the other's closed orbits. Just give it enough energy, can't get bound. If you want to, see if you can get a bound state here with a negative energy. But that's really optional. Okay. Point 7. How do you determine the scattering angle? This is very interesting, and you have to be careful. I recommend you look for a function, whatever language you're using. I like this function A tan 2, because you can get the scattering angle by the arctangent function. But if you take the arctangent of Vx divided by Vy, nope, it should be the other way. Vy divided by Vx, that's usually what gives you the tangent, depending how your axis is. You can sometimes be divided by 0. If you divide by 0, the computer gets very unhappy. You don't get any answer whatsoever. Okay? So here, what you want to do is wait till your trajectory is far away from the target region, y equals plus infinity. And this function lets you separately say what the x and y components are you're trying to take the arctangent with. And it also tells you what quadrant your scattering angle is in. So rather than be limited to plus and minus 90 degrees, it'll actually use all 4 quadrants, so you know just where the scattering's taking place. So that's very important. So if you've never seen the A tan 2 function, this is a good chance to look it up. It may be called something else, but that's what you want. Okay? As we saw, where is d theta dB discontinuous? And you're sure it's not numerics, it should be the physics. Very important. Run both attractive and repulsive potentials, and run various energies, which means velocities for the incident particle. How do you determine what energy should be? Well, if you look at those peaks on the potential, they had the maximum energy at the potential is e to the minus 2. So that's a number which sets the scale for this problem. So you want energies which are smaller than that and larger than that to see the effect. Okay? And finally, and let's call this optional, for those of you who have studied classical mechanics, one way of studying this problem is to look at the time delay. Calculate the time delay as a function of impact parameter b. So imagine there was no potential. For any given velocity, you know how long it would take to get from minus infinity to plus infinity. This might be 2 to, plus 4, minus 4 to plus 4, say. Okay, you know what the time is. Distance divided by velocity. Then put the potential in, calculate how long it takes to get between the two as a function of impact parameter. That function, which is measurable experimentally, and you can calculate very easily, is a nice way to compare to experiment that has chaotic properties as well. So, time to send you on your way. Get to work, go to the lab, make some chaos in the lab. Let me end by saying, this is fascinating. Use the applet. We have had maybe 3 or 4 students who've been so interested in these results when they've gotten them. These are grad students. By and large, they've gone on to do master's and PhD theses studying this problem. Most of them have studied it for the master's undergraduate theses. Classical, the PhD thesis was actually a quantum version of this to look for similar quantum effects where you'd compare quantum and classical and see if there's similarities. So it's very easy numerics. It's just applying what you know already, but it has real research, forefront research level applications even now. So thank you for listening. I'll see you again soon. Don't forget to look at both lectures. Bye-bye.